Okay, Calculus BC, we're going into our second last chapter of the semester. Lesson 6.1, you can see our learning target. I can find the area between two curves. Let's read this little theorem here. F and G are continuous functions, and F is always greater than G of X. F will then be above G of X, on your graph. And that would be true for every X value between A and B. The area is just going to be found by this integral right here, from A to B of f of x minus g of x dx. And what I definitely want to say right now is you're going to hear us make mention of this quite a bit. You can always refer to top minus bottom. Top minus bottom. Here's what you can definitely see happening. You might think, why are you talking about top minus bottom? Well, you look at this top curve. If you look at f of x, you could see that we could make ourselves a rectangle right here. Let's just say that I'm making this rectangle in red. And for g of x, if we were to make a rectangle here, let's just say I had that in green, that would be like so. Well, the area between those two curves, if I were to highlight that in there, you could say it's really the top rectangle, the big rectangle minus the little one. It's always the top minus the bottom. That top function minus the bottom is going to give you the area that you're looking for. And if you hold on to that, you're going to be in really good shape. Now, I want to tell you this is also true even when you have a region that falls below the x-axis. So very often kids look at that and they'll say, so you're telling me if we saw this integral, if we wanted to find this area, you're saying it would be from A to B of the top function, what's bounding the top, that's f of x minus g of x dx. You're saying that's going to be the area bounded by the curve. Yes. Now, sometimes kids will say, okay, I don't know if I believe that in the same way because, look, if you go to F first, you'd get a rectangle that looks like that, wouldn't you? And then you could say, then if you went to G, and if you were drawing that in a green rectangle, you could say, well, that would be this one. And you'd be saying, now look at that. You're doing top minus bottom. You're taking the Fy value minus the Gy value. Someone could look at that and say, are you sure you're going to get the area here? Won't you get something negative?
It's negative. The area is negative.
See, no, it actually won't. Look at this. Let's just say that the red rectangle had a value of -3, right? Let's just say that down here for G, it was -8, right? Well, if you did your top minus bottom, wouldn't you get -3 minus -8 there? And look what happens. That would be a positive value, wouldn't it? That'd be a positive value. Top minus bottom is always going to work out, right? You always want to have top minus bottom, and you're going to find the area between two curves. So look, we're going to take a look at some examples here. Draw yourself a picture. Draw yourself a picture. Here's what it will look like. Y equals -x squared. That's an upside down parabola. You don't have to draw it perfectly well. Just sketch it out to get a general idea. Y equals 1 over x squared. That's what we called our volcano graph, right? Y equals 1 over x squared. It looked something like this. So, you could more or less say it's going to have this kind of a shape. But I want to have a region bounded between also x equals 1 and x equals 2. And that's going to also enclose that region right there. If I gave you x equaled 1 as a line, you hopefully remember the mnemonic VUX. And there's also the mnemonic HOI. VUX stands for a vertical line with undefined slope, and x equals a number. Here you have it. You've got this region enclosed right in here. So you could see that you're integrating from what boundary to what boundary? You're integrating from x equals 1 to x equals 2. Now you can even see at the top of the screen here, we always want to do top minus bottom. What's the top function that we have for our boundary? That's 1 over x squared. That's your volcano graph, isn't it? And then we'd say top minus bottom, then you'd say your lower boundary is going to be this negative x squared. Guys, at the end of the day, this becomes just like a routine integral that you've been doing so many times. Once you set this up, the rest of the problem, you just have to, work it out. You could say, hey, that's x to the negative 2, and this is plus x squared. We just have to do the fundamental theorem of calculus. So what's the antiderivative of x to the negative 2? Well, bump this up by 1, and you get x to the negative 1, right? Then you divide by a negative 1. You'd really get negative 1 over x, wouldn't you? Right? That's negative 1 times x to the negative 1. And then how about this x squared? What's that antiderivative? We'd get, 1/3 x to the third, or x to the third all over 3. And then you just have to finish that up. You plug in your 2. You'd say, well, I've got a negative 1/2 plus 2 to the third all over 3. I'll say minus, we'll plug in your 1. You get a negative 1 plus 1/3. Now it's just number crunching, guys. If you can finish that up, hopefully you can do that quickly. Here's negative 1/2 plus 8/3. Inside here, negative 1 plus 1/3 is actually negative 2/3. So when you add that, you'd get a plus 2/3. Now, before you always try to get a common denominator between everything, you can also, look to see if maybe, just maybe, the 8/3 and the 2/3 could get combined, and they can. You could just combine those together to get 10/3. And then what? At that point, let's just combine the negative 1/2. If we multiply by 3 all over 3, we'd get negative 3 all over 6. Multiply by 2 over 2, you'd get 20 all over 6. Final answer will be 14 all over 6, but reduce that and you should get 8/3. Okay, sorry about that. Little correction, by the way. Negative 3 over 6 plus 20 over 6 is 17 over 6. So at the end of the day, that's really all you're doing. You're just trying to really get the correct boundaries, top minus bottom, and then work that out from there. Let's do another problem. For example 2, this might be a little bit more tricky. Look, you've got y is equal to x plus 6. You've got y equals x to the third. You also, if you were solving this, it wouldn't take you too long to see that you'd get negative x all over 2. So as we graph this, you're going to enclose a region. That's pretty much your standard situation. Notice they don't give you x values to work between. So when that happens, expect to enclose a region. Now, y equals negative x all over 2, of course, is a line with negative slope. And you'd start at the origin right here, and you have your negative slope. You go down 1, you go right 2, and rest assured, it's going to have a slope that looks something like that, right? Now, as you're working out y equals x plus 6, you can say, well, somewhere up here we're going to have a y-intercept of 6, and I'm going to have a slope that's positive. I'm going to have a slope that's equal to 1. So, expect us to see something that looks more like so. And notice I'm not even drawing anything close to a super detailed graph, deliberately at that. You always could. Look, if you had y equals x to the third, hey, that's going to be a function that looks something more like that. Now, once you've looked at the three curves, I hope it's going to jump out at you that you've got an enclosed region like here. Now, what makes this problem a little bit different from what we just saw earlier, you're going to say, no, wait just a minute, you didn't give us boundaries to integrate from. Like the first example, they said go between x equals 1 and x equals 2. I've got this yellow region. Of course, the big question is just where exactly are we going to be integrating from? So we've got this intersection point. That's coming from y equals x plus 6 and y equals negative x all over 2. You could, real quickly, set these two equal to each other. Look at that. Because if you're doing that, what's really happening is you're saying, I want to know where those two lines intersect each other. And then you can solve. Now I can minus an x from both sides, and we'd get 6 equals, well, this is 1 over 2 minus 2 over 2. I'd get negative 3 over 2. And, now I can multiply both sides by negative 2/3. And it doesn't take too long to see the negatives are canceling out. Looks like we'd be at x equals negative 4 if I'm not mistaken here. Could we also find the y coordinate? We could, but we don't even really need it at this point, do we? And then you could say, well, wait a minute, what about this other curve right up here, the cubic, y equals x to the third, intersecting y equals x plus 6? You could think, well, wow, as I work that thing out, y equals x plus 6 and y equals x to the third, what can get kids very nervous is when they try to set this equal, they can say, wait just a minute, I don't know how to solve something like that. Now, by the way, you did solve that in AMA, where you'd get everything on one side. You'd use the rational root theorem. You'd try to find what zeros would make that equation true. Now, there's a better way, there's a quick way, and this is called solving by inspection. Here's what I'm talking about. If I plug in x equals 1, is that true? No way. How about x equals 2?
Yeah.
Cha-ching, that's it. Look at that. Look at that. 2 to the third. So that can work for so many of these curves. It's a time saver. You just try some integers. I'm saying integers because sometimes you might want to try a negative value. And if you'd say, hey, that works, it's wonderful. Now listen, right now as we're wrestling with this, you can say, wow, how do I keep going here? Notice it's always top minus bottom, but I'm sure you're seeing there's a problem. The top, sometimes kids will say, oh, there's no problem. Look, the top is that line. The bottom is the cubic function. Is that always true? No. And I'll tell you why. If you look over here, the top is still that line, y equals x plus 6. The bottom is not the cubic function over there, is it? It's always top minus bottom. But the problem is my bottom boundary changes over here. Look, I've got two separate regions that I'm going to have to work out. I've got this green region where the bottom boundary is different. So I'm going to integrate the green region. I'm going to go from negative 4 to what? Negative 4 to 0. What's the top? The top is x plus 6. What's the bottom? Negative x over 2. Then I'm going to say, now wait a minute, I'm going to go from 0 to 2. What's the top? X plus 6. What's the bottom? X to the third. And it's at this point that we could work those integrals out and get our solutions. This is a problem where one region doesn't suffice because the bottom boundary changed. I had to set up two integrals to make this work.